Hi everyone, I'm Lindsey Batterton, and for the past semester, I've been working with Dr. Miller as my capstone advisor. For my project, I've been researching black holes and general relativity to gain a better understanding of the first photo that was ever taken of a black hole. It was published about 3 years ago, which is still fairly recent for a new discovery in physics and astronomy. So the goal for my project has been to learn more about the physics of a black hole and describe the photo. Here's an outline of what I'll be talking about today. First, I'll define what a metric is and how it's useful for general relativity. And then I'll give some background information on black holes and describe how the Kerr metric is useful for black holes. The Event Horizon Telescope was used to take the first image of a black hole, so I'll describe how it works, and then I'll show the image itself and explain what's being shown. General relativity is a field of study that was developed by Albert Einstein in 1916. In general relativity, or GR, a metric is an equation that describes a specific region of space-time. Space-time is often called the fabric of the universe, and it can be curved by mass or energy. In the photo on the left, it shows flat space-time, which is completely empty. And then on the right, it shows how mass will curve space-time. The lines in the middle of the grid look more stretched out, which shows how distances will change due to the curvature of space-time. And when this happens, time will also begin to slow down. The equations for Einstein's theory of gravity have different solutions to them based off of the type of space-time that you're looking at. The Minkowski metric is used for flat space-time. The Schwarzschild metric is used to describe the space surrounding a spherical and stationary object, which in theory can describe a black hole if it's stationary. And then the Kerr metric is used for spinning spherical objects. And since black holes, most of them, if not all, are known to be spinning, the Kerr metric was most relevant for my project. So what is a black hole and how are they created? They're formed after a supernova, which happens at the end of the life cycle of a star. After a few billion years, a star will burn through most of its fuel and then explode. When that happens, the core collapses in on itself and creates a singularity. Around the singularity is a boundary called the event horizon, and anything that passes through the event horizon is unable to escape. This includes mass and light particles. Light is made up of particles called photons, and they're the fastest moving particles in the universe. But the gravitational force from a black hole is so strong that it's able to trap light within it. Here's a diagram showing a black hole. In the center is the singularity, and that's where all the mass is concentrated. The circle around it is the event horizon. This is where no light can escape. Black holes can have different amounts of mass depending on the star that created it, and depending on how much mass is consumed from its surroundings. The more mass that a black hole has, the more that space-time will be warped. This equation is the Kerr metric. It can be derived for spinning spherical objects. And since black holes are known to form from supernovas, it can be assumed that they have a high angular momentum and are spinning, so we use the Kerr metric to describe them. It's a very long and complicated equation, but I'll explain a couple of the terms that are in it. The letter G stands for the gravitational constant, so that'll be the same throughout the whole equation. And then the letters M and A stand for the mass and angular momentum of a black hole. So to use the Kerr metric, you would enter in the mass and angular momentum for a specific black hole, and then you'll be able to find how distances are affected, and how much time will be slowing down due to the black hole. The Event Horizon Telescope was created specifically to take images of black holes. It's actually made up of 8 different telescopes, and they're spread out on the Earth. How they work is they'll all take one image and collect data on one specific object in the universe, and then later they'll combine all of that data to form one clear image, and this allows us to have a higher angular resolution to be able to see something as small as a black hole. This is the image that the EHT was able to create. It's the first ever image of a black hole. It was published in 2019, and it's showing the supermassive black hole M87, which is in the center of its galaxy, and it's located about 53 million light years away from Earth. In the center of the photo is the shadow of the black hole, and this is where light is unable to escape. Surrounding that is a glowing disk, which is called the accretion disk, and this is made up of gas and dust particles that are orbiting the black hole. So we're unable to directly see the black hole, but we can see particles that are around it and locate where it is. This is the same photo of M87, but with some labels added to it. The circle on the outside is for the innermost stable circular orbit, which is abbreviated as the ISCO. And this is where particles will begin to completely orbit inwards towards the event horizon. And this is why the shadow of the black hole starts at the ISCO instead of at the event horizon. Further in is the photon sphere. This is a distance where photons can make one complete orbit around the black hole. And the innermost circle is about where the event horizon would be for M87. This is a diagram showing the possible trajectories of particles around a black hole due to its curvature. The lower red line is showing that when they're pointed towards the center, they will be absorbed by it. And then the middle line is showing where the photon sphere is. This is where they can make one complete orbit around the black hole before being drawn inwards. And then the line on the top is showing that the black hole is curving space-time so that when it's far enough away, it can still be bent around the black hole. And these are particles that can leave the area and be captured by the EHT to form the photo that was shown earlier. So why is it important to study black holes? Most of them are formed from supernovas, but the formation for supermassive black holes is still unknown. And black holes allow physicists to study the laws of gravity and ensure that the equations that they're coming up with are accurate. And then since a supermassive black hole is in the center of most galaxies, we assume that they play an important role in how galaxies form and how they change over time. And then recently, about a week ago, on May 12th, the EHT released the second photo ever of a black hole, so I thought I would include that in my presentation as well. It's also a supermassive black hole, but it's in the center of our own galaxy, the Milky Way. It's showing Sagittarius A star, which is much smaller than M87, but this allows physicists to study different sized supermassive black holes to compare and contrast them. And it's exciting that the EHT is still releasing new photos, and in the future they hope to create clearer images of black holes and possibly even create videos of them to show how they change over time. And that concludes my presentation. Thank you all for listening.
Thank you very much. Do we have any questions for our speaker?
What was your favorite thing about researching black holes?
I like learning about the accretion disk because I thought it was interesting that not all particles go into a black hole.
So are black holes like constantly gaining mass? And if so, like as they pull things in, are they constantly gaining mass? And if so, like is that Kerr metric?
The Kerr metric.
Does that somehow take that into account?
Yeah, so if they have an accretion disk, they'll be absorbing more mass, and the Kerr metric would change over time because the mass would be changing.
And a slight update, we forgot to have you introduce our speaker.
I know, I was wondering.
We've had 2 years off. There's going to be a few hiccups.
Yeah.
Okay.
Sorry, my next student's next, so I
Perfect.
can do them both at the same time.
Anything else? Okay, so let's thank our speaker again.